and say hello to this fourth session, I think this is. Unfortunately, I was not able to secure an input talk for today. I had approached some of the speakers I had outlined in my original email, but unfortunately, all of them have deadlines coming up for project proposals and what have you right now, so they didn't feel comfortable with giving an input for this, especially since I always advertise with a 3-hour time limit, and I told them, you can only do one, but then they felt bad only giving a 1-hour talk instead of 3. So I'm still in contact with them. I hope I can get some input talks for the other dates where I had planned it. If I can't, pending the success of today's session, obviously, would just argue in favor of making these input sessions into sharing sessions of what we work on with Bayes, how we do it, troubleshooting, exercises, a bit more hands-on sessions. And that being said, I think it's best we jump into the first of these 5 questions or 5 exercises that we were looking at for today. That being said, today is going to be a short session because we only had those 5 exercises. So if anyone here, because we've got a few new faces, if any one of you, and the old faces as well, feel lost on something, we have a lot of time today and we can totally accommodate any kind of question. And please never hesitate to ask questions. Because if you think it's a dumb question, then probably 60 or 80% of the audience will have the same question. They just won't have the gall to speak up about it. So with that being said, we've got 5 questions. We are 5 people. So I fully recognize that not everyone will have solved all of the questions. And I suggest we just start in the order that you are on my Zoom screen. And if we hit on a question with you that you haven't managed to solve or haven't had the time to solve, then someone else will just take over. So Anna, you're up first with the first question. If you want to share your screen and your solution, okay, that'd be fantastic.
No problem.
Hey, Yuming, you fixed your camera. Nice to see you.
Hey, nice to see you.
Okay, so can you see my screen?
Yes.
Is it the correct screen? Do you see the R stuff?
We are seeing your HTML output. Yeah. So that was the HTML
yeah,
view.
Okay, that was fine. Exactly. Yeah, so I'm going to try share this. It might be a bit small for you. I hope you can read it.
Totally fine on my end.
So the first question was about refitting the model, right?
Yes, exactly.
I renamed them, so okay. So it was about refitting the model from chapter 4, but omit the mean weight X bar this time. And then compare the new model's posterior to that of the original model. And in particular, look at the parameters. So what's the difference? And then compare the posterior predictions of both models kind of as a second part of it. So I can show you also my R.
Yes, if you could walk us through a refresher of how the model is fit and how it's defined.
Exactly. So this is just where I load the data that they actually define in the chapter. So when you look at chapter 4, this all makes more sense. This is basically just typing what they also typed in there. And then here's where I define the X bar. And this first model is just the model how it is in the book. There's no changes applied to the model whatsoever. You see that the X bar is still in there. And this function is basically what gives us this table that I also had in the HTML. And they said specifically we should look at the parameters. So alpha, beta, sigma. You have here the mean, standard deviation, and so on. So this is no changes made whatsoever. And then this is where the input comes. What I had here, the X bar, is just removed in this model. So the new model has no X bar in there. And when I then look at the model parameters, it looks a bit different. So when we compare alpha, the mean of alpha here, it's 154, while here the alpha is only 114. So that is actually where the change happened. And not only the mean change, but also the standard deviation. So it's only 0.27 in the unchanged model, while when you omit X bar, it has broader standard deviation of 1.9. Interestingly, the other parameters like beta and sigma, there's slight changes, but not really any big changes at all. So that's what I found out for the parameters. Exactly, and then I plotted the curves, the posterior predictions. I'm going to open the HTML because it looks nicer there. This is the posterior predictions when you do not change anything, or when you omit X bar, it basically looks the same. I don't know if there's actually any change in there, but it looks pretty much the same. So that is actually how I answer this question. I wrote myself a question underneath saying, what do I take from this? So that's actually a question to you.
Cool. First of all, thank you. Very nice, clear presentation. Does anyone else want to weigh in with what we can take from this? Because I think I have an answer here, and it's all to do with the interpretation of A. So A is our intercept. In both models, it's the intercept. But what it actually identifies when we put it into real world terms is different. Because if you take a look back at the model specifications in R, I think it becomes a bit clearer when we look at those. So if you look at the original model, so specifically line 52, in line 52, that mu is going to be alpha, our intercept, when our individual that we look at has the mean weight. So this is the average height. So alpha in our first model is the average height for the average weight. Now, if we look at line 75 in your second model, by omitting this centering parameter of X bar, alpha now can only be the same as mu if weight is 0. So that means now alpha is the average height of a person at 0 kilogram of weight. That's why you get this lower estimate in your second model, because now it means something else. But when you plot the actual predictions or the actual model fit, it's still the same. Yeah. Just where you would plot alpha, the intercept, on your x-axis has changed. So I think that's the takeaway from this. If you center or not, you can still make predictions the same way, but the interpretation of different parameters on which you have applied centering might change quite drastically.
Okay, just to make this clear, if you interpret your values in the end, what it means to center or not to center.
Yes, exactly.
Okay, cool. Thanks.
I could be wrong, but I think that's the takeaway.
That makes sense.
It makes sense to me, at least.
Yeah. Okay,
all right.
Sharing them?
Yep. I'm next in line on my screen, so I'm just going to take over with practice 2. And practice 2 is actually one that I ran into a bit of troubles with. So we already discussed this before we started the recording. We have taken these exercises from an older print version of the Rethinking book. And because of that, even though all of these exercises can still be run, it seems as though, and unfortunately we're missing the person who owns the print version, the older one. He's not here right now.
Actually, I do own the new one as well.
Oh, okay, coolio. I'm only slightly jealous. It seems as though the model that they're after in the newer version of the book is one where we look at temperatures in March throughout the years in Japan, whereas in the older version, which this method, or not, sorry, not this method, but this exercise seems to target, we look at the date of cherries blossoming in Japan through the years. So that is day in the year. I have solved this for the temperature because that's the model I wanted to work with, because that's what was in the book. And I noticed way too late that they were probably talking about a different model because it was a different version of the book. So I'm going to walk you through what I've done, and that is going to be this screen. So for practice number 2, I'm just going to quickly read out the exercise itself. In the chapter for that spline model, where we looked at cherry blossoms, we used 15 knots. And in my case, I look at the temperature, whereas the older version of the book seems to look at the date in the year where cherries blossom. Now we are supposed to increase the number of knots and observe what happens to the resulting spline. In addition to that, we should then also adjust the width of the prior on the weights, so that's the weights of the different basis splines, by changing the standard deviation of the prior, and then watch what happens. What do we think what do you think the combination of knot number and the prior of the weights controls? So look at the results and think about how this came to be. So for my answer, I took, and this is all targeting the newer version of the book, I looked at pages 118, 120, and 122, where I found a bit of code for this, which I mostly just copied and pasted over. I load the Rethinking library, I load the splines library so that I can define the basis splines. I then load my actual cherry blossom data, save it as a separate object, and then only retain those rows where I've got temperature records. So where I actually have data, because NA values just aren't handled quite that well by quadratic approximation, which we use further down the line. So then I define a function for myself, because I really only want to control 2 parameters here. One is the number of knots, and one is the standard deviation on my prior for the weights. So what I do is I write a function. This function works off of number of knots and standard deviation. In this function, first I identify the knot list, which is just a quantile from 0 to 1 with these numbers of knots right here. So if I define 15 knots, for example, which is the default in the chapter, I select the quantiles from this year range. So this is where I want to have the splines, and then have a sequence from 0 to 1 in a length of 15. I remove the first knot and the last knot because those are the goalposts. So that's the absolute beginning and the absolute end, and that's not really of any use for my splines in the end, because the knots are the ones where I want to have overlaps. That's what a knot is. By itself, when just one function starts right at the beginning and when one ends right at the end, that's not really all that useful. So then I define my basis functions by the years that I have with the knot list that I have. I give it a certain polynomial degree. I run with polynomial degree 3 because that's the same as in the book. I tell it to please do this with an intercept. And then I run my quadratic approximation exactly the same way as in the book. So I'm not going to go through this too much here. Only importance to point out yet again, I am looking at temperature, which is normal distributed with a certain mean and a certain standard deviation. And this mean is modeled with an intercept and with weights on our basis splines, which we have to do a matrix multiplication on, which is this bit right here, so that we have the additive effects of multiple different basis functions with respective weights. More on that in the book, and we can gladly talk about this some more right now as well. So I give this a list. In this list, I give it, for example, the standard deviation that I want, because that hasn't come in yet, only right here. I've specified this in the beginning of the function. Now I'm handing it to the quadratic approximation with this data equals list argument. Then I compute my 97% posterior interval, the same way it's been done forever so far. I plot it right away, and now I'm ready to call this function multiple times. So what I do now is I start with the base model that was in the book, and I just do my cherry spline with a number of 15 knots and a standard deviation of 1. That's exactly the same plot as we would obtain through the code that was in the book. In the book, they neglected or purposefully omitted this plot. That's exactly what you get when you just run all of the default values from the book chapter. But now what happens when we increase the number of knots? So as we increase the number of knots, we can already see, especially right here in the beginning of the plot, that the function becomes more flexible. Or as McElraith says in his lectures, it becomes more wiggly, which is spot on scientific lingo, if you ask me. So if we add a few more knots to this, so we've gone from 15 to 20, now let's double the original number of knots. With 30 knots, you can see that this has become even more wiggly. So what the number of knots do is they, and I've written this down here, they control how flexible our function is, which means that if we increase the number of knots, we should be able to fit any kind of function better to the data at hand. However, we should be wary of overfitting, because especially when we try to predict beyond the ranges of this, we can't make use of all of the information in the middle anymore, because the weights of these central functions here will be 0 by the time we reach these end knot points. And predicting using splines beyond the range of the data at hand is an inherently bad idea. So there's a trade-off here between getting to really explain the data at hand very well, but losing all predictive capabilities. That's what knots do, to my understanding. Now, as soon as we change the prior weights, we just have to change our standard deviation parameter. So I changed that from 1 to 10, and then I changed it to 1,000, but I don't see a difference. And I legitimately don't know why. I am quite flabbergasted by this. I also made a note of this down here, that for some reason I cannot see a difference, but what I would expect is our function to become more flexible when we raise the standard deviation, because by raising the standard deviation, we will decrease the weights so they approach 0 more closely, meaning that throughout the entire range, all of the weights should be pretty much non-existent, meaning basis functions don't really smoothly transition into one another. So we should get more or less a straight line, because it's just the average of all lines at all points. That's what I thought would happen. It didn't, and I don't know why. I assume I may have miscoded something, but I just couldn't find where I went wrong. And for this, I think it's good if we go to Gregor's website. So that's our chap who is unfortunately missing today, but who has
Just real quick, excuse me.
Yeah.
I have my function gets smoother, but I changed. If you go back to your R, what you just said, open.
Yes, please.
With a W, when you define it, it was before, I think it was 0 and then 10, right?
Yeah, it was 0 and 1.
I actually went 0 and, okay. I think it was for me, I actually did change it, and for me it becomes smoother. I mean, I can show you what I have in terms of.
I'm going to stop the screen share and give it over to you.
Okay, because I did it a bit. My code is longer. I did it step by step, but maybe that helps.
Sure.
So I actually did not only plot years against, and I did not use temperature, but I actually choose days of the year. Mm-hmm. So at the bottom, it becomes more like what you did. Yeah, this is basically more similar to yours, but as you see, it's cherries against days of the years. So yeah. Temperature. So I also tried to actually do the other plots with years against basis and weight, and just years against the basis. Mm-hmm. Maybe this also helps a bit when you increase your knots, like the frequency also becomes higher here, especially towards the end. So that makes you to understand what's going on. For the basis times weight, I'm not sure I did it right because it looks really weird. But for the knots, when I see, this is the one where I didn't change the standard deviation. Mm-hmm. But this is the one with the same knots, but I changed the standard deviation, and mine becomes smoother.
Okay, so what I thought, so what I thought would happen did happen. That's nice. But could you show me the two model specifications, or could you show us these two model specifications? Is everyone else still following, by the way, or have we completely lost you? Because it's only been the two of us so far.
I think in the first session it's really mean to start with these
Yeah.
exercises. I think Rivan, you wanted to say something.
It's okay. I can still follow it. Yeah.
Good.
Perfect.
Glad to hear that.
Where are we? No, this is a. See, I did it more like manually defining my knots from 15 to 200 and so on and so forth. So this is the first plot. The second one, yeah, this is where I have them. And the models you need, right? Yeah, the models.
Yes.
So this is the one from the book, basically. Where I thought it was the W in my book is the norm 0 and then 10.
Yes, they have the 10 on there because now they're looking at days where you just have a bigger standard deviation than on temperatures. I think a standard deviation of 10 on temperatures in Celsius would be quite enormous.
See, and I actually went down. I chose 2. And this is when that happens, what you expect it to happen. Not by increasing it, but actually going down.
Oh, interesting.
Yeah. So that if you, I mean, you chose a really high number, 1,000 or something. I just went a few down, and then it happens what we thought would happen. So if you try that, maybe that also changes how your graphs look like. I
am going. Maybe I had a lapse in thinking then. Give me 1 second. I am just going to go over to R. And bringing that over to this screen. And now I'm going to share this with you. There we go. So this is my code for it. And I want to go to practice 2. And in this one, I've got my function. Just run everything up to that point. Yeah, because I just increase. What happens if I decrease? So that's the base plot.
There you go. See? It also becomes flatter, but this is really flat.
Yeah, wow. Okay, so this was literally just me having a lapse in thinking, but where did that come from? So I hope you guys don't mind me being all confused now for a hot second here. Because these are the weights. And if I just do a normal distribution around 0 with a standard deviation of 1,000, we get down to a weight of 0. With 100, also still 0. That's a really small number. So now the weights. I think I know where my lapse are. Yeah. It's the other way around than what I thought it would be. We need higher weights so that the effect of a function stretches along a wider range in our actual plot. So if we go back to the plot and we flip back to this original first plot, because we have really tiny weights here, we have this smooth transition of one into the next because the weights don't extend far on the x-axis, if I get this correctly, or their effects aren't very big. But as we get stronger weights, the algorithm has a harder time finding smooth transitions, and that's why we get this.
Yeah, that makes more
sense. Cool. That is fantastic. So I get to update my thinking here. Nice. Cool. I'm just glad it also works as expected then with the temperature data.
There you go. Yeah.
Cool. I'm going to stop my share here and
my question, like, would you also get like a straight line if your spline starts at the very first and ends at the very last knot, so that you are fitting like the algorithm to the entire thing, not separating into chunks?
Well, then you're not really running a spline anymore. Then you're just doing a linear regression.
Okay, but it will be linear in the end.
Yes.
It will do the same trick as the weight function.
Yes. So if you look at if you look at the space between two knots, I think that's your question, right? So in your hypothetical, we just have two knots, one at the beginning, one at the end. Cool. In that case, it all comes down to how you define your basis. Let me share my screen again. Going over to this. So the way I define those basis splines here, let's say we have a knot list with just two entries, the absolute first and the absolute last data point that we have. Then we will only get one basis function. However, this degree here is what controls how that function looks like. So that's the polynomial degree. We could just set that to 1, and then it's just a linear function. However, if we keep it at 3, we will try to fit a polynomial function of degree 3 between the first and last data point.
Got it.
Cool.
I mean, the interesting thing I think about the entire chapter 4 is it's basically about linear regressions, linear models, but he's kind of splitting it up in so many ways that you understand or sometimes do not understand what he really means. But it's far away from what we learned in linear model.
I think he does such a great job of, if you guys who came in fresh here haven't read chapter 4 yet, I think you should, even though it's a bit long. It seems like this will be a chapter we will reference again and again and again in the coming sessions, because he does do a very good job at explaining some basic stuff that you thought you understood in a way that you actually understand it now. At least that's what I felt like when I read through it. So moving on to practice 3. Except for Anna and myself, who managed to solve it? And don't worry if you didn't. That's cool. Ridwan and Yuming, looking at you guys.
For me, I didn't manage to solve it.
All good? All good. That's totally fine.
Actually, I just start to read the book, and I have finished the chapter 1 and chapter 2. And because I have doing the data-driven before,
Right.
we have this. I have this thinking about the frequency and the Bayesian, because I want to use the Bayesian method to build up the Bayesian network to solve the causal problem with my research. Yeah. So yeah, I will follow up your. So I just want to check
Don't
that.
worry about it. Don't worry about it. But if you think we should make some things clear in our explanations here, just speak up, because you'll help everyone.
Yeah, thanks.
Cool. Anna, did you manage to solve that one?
I did, but I actually did it the easy way because I thought some person might actually choose the hard way to do this linear regression, right?
Yeah.
So I bet you did it different than me because I choose the easiest way I could actually do it. I will show you.
By you did it the easiest way, you mean you fit a linear regression instead of polynomial or spline?
Exactly.
Yeah, I did the same.
You did the same. Okay, so we can compare.
Yeah.
Well, this is my linear regression. It's cherry days of the year against the temperature, and yeah. And it's this is really the old way. This is not the Bayesian way. Right. This is why I thought we could compare. For me, it's absolutely highly significant. You see the 3 stars here. And this is the way I would have done it before, but I'm pretty sure that you can actually compare it then to the Bayesian way, if you've done it that way. Yes, you can. Could you quickly resume screen sharing, or just tell me your different parameter estimates? So what was your intercept and what was your beta? My intercept is 123, right? Wait, where do I see mine? That's temp, so negative 2.994. Oh, that's fantastic. Did you center your variables by any chance? No. Ah, this is fantastic. Cool. Because sorry, I get really giddy about these things.
So I am just going to share this screen. So what I've done for this is I went the Bayesian route. And first thing I did was I loaded the data anew again. I only selected the columns for day and year and temperature because I didn't need anything else. Then I removed everything where there was an NA and a euro because I need complete cases between the two. What I then did was, just because I wanted to see how it looks in scaled space, because I wanted to use centered variables afterwards, I just did a quick look at what my data looks like. So I center my temperature data by applying the scale function in base R, and then I plot this bad boy. And I get the exact same kind of structure as you did in your plot, only that my temperatures here on the x-axis are centered right now. And from this plot, I thought, okay, I can see a negative relationship here. It's probably not very strong, but also there's so much noise around this. If I apply a polynomial function or a spline function, both of those approaches will try to somewhat arbitrarily, as far as I'm concerned, model the noise as well. And I didn't want that, because that would make interpretation so much more difficult and so much harder for me to understand whether my model is doing the right thing. So what I thought was linear model. Let's do this. Also, I did all of this half an hour before we met today, so I was really in a time crunch. And I thought, linear is going to be the fastest to implement. So what I do is, again, I find my X bar, so I can center my variables in my actual model right here. I do the model, identify some priors where I think it's probably going this direction, probably this strong, just from looking at the plot. And the priors aren't even that important here because this is roughly 800 data points. So the data will probably outweigh the importance of the prior by quite a bit. I haven't played around with it though. I saw that this worked and thought, oh, that's fine then. So then I look at my output. And in my output, we find that our intercept, for me, because I've centered variables, I think, is 104 or 105, meaning an average cherry blossom event will happen on the 105th day of the year when the temperature in March was the average over all temperatures in March. Now, the way we would interpret your intercept, that comes back to question 1, would be cherries would blossom on the, I think it was 123, on the 123rd day of the year if the temperature in March was 0. And because we have this negative relationship here, meaning that if the temperature increases, the cherries blossom earlier, this makes total sense. Because by having decreased our temperature that we use for our intercept modeling, we increase the date in the year when the actual blossoming happens. And I would wager to guess, as a matter of fact, why don't I just do it? Let me do all of this. I'm just going to rerun my model without the centering, and I'm pretty confident that I will then arrive at 123 as well. And there we go, 123 right there.
That's cool to see.
Ah, that's magic, isn't it?
Mm-hmm.
Sorry guys, I get really excited about these things. That's fantastic. So when I then plot this, and I wrote a function for myself for that earlier, because I didn't want to always type out how to identify the different intervals and what have you, we can see that, yes, there's a negative relationship. These are our parameter uncertainties right around this here. So that is the uncertainty of the actual slope. And the wider margin that you can see here is the uncertainty of our predictions. If we were to predict when this is going to flower. And you can see that we can explain when the cherries blossom, but we're definitely not certain of it. And that's my takeaway from this. I think it's pretty cool to see that Frequentist so far still does the same stuff at Bayesian.
Yeah, that's cool to see.
And practice 4, I haven't gotten around to. because that is where I ran out of time. So I think what I'll do for now, because practice 5 is super short, I'm just quickly going to go into practice 5. I'm going to explain how I did practice 5, then we can probably look at your solution if you've gotten around to it, Anna, because you will have probably used a different model. Okay. And I cannot guarantee that this is correct either, because I got done with this literally a minute before this meeting started, so I don't know.
I have
And once we've...
Sorry.
No, go ahead.
A quick thing to the practice before. So the model ANNA, the standard linear model thing without centering, predicts that if the March temperature is 0, we have the flowering at day 123, roughly day of the year. And in your centered model, it's at day 100 and a little bit earlier,
105.
And the mean temperature of March is like 6 degrees, so it actually fits. Like if per degree of warming we advance our flowering onset by 3 days, then if we multiply the mean temperature of March 6 by the slope per degree, it fits. So then both intercepts become equal.
Oh, that's nice.
So just
that's cool.
the slope thing in there.
Yeah, that is so, excuse the language, fucking cool. But yeah, thank you so much for that, Bernd. So going into practice 5, and I suggest we take a short break after question 5. I'm going to put the link to Gregor's webpage where he solved question 4 into the chat, so we can all have a read of that on our own time for about 45 minutes, and then we reconvene and we talk about what we think of his solution. So practice 5. The cherry blossom spline in the chapter used an intercept. That's parameter A, but technically it doesn't require one. The first basis function could substitute for the intercept. Try, refitting the cherry blossom spline without the intercept. What else about the model do you need to change to make this work? And I don't think I got to make this work, because what I did was just loaded the data in again, selected for the complete cases, all of the stuff I did earlier. And then the only change I did is in this line right here. And I just took away this A. And now looking at it, I think I might have to set intercept to false for the basis functions. So if you just bear with me, I'm going to go into R, because my output looks the exact same as my initial function. And that didn't quite make sense to me. So what I think I might have to do is also define basis functions without intercepts. And I'm just going to run this block. Yeah, and that's it. That makes sense now. So in order to make a spline model without an intercept, we can't have an intercept in our deterministic function, which is here on line 247 on my end. And we have to set intercept equals false on line 244 on my end when we define our basis functions with the BS function from the spline package. And then this does quite make sense, that because we haven't modeled with an intercept, we just get this first base function that we have just extrapolated all the way beyond the limits of the plot. Yeah. I think at this point, I'm going to quickly hit pause on these